Doppler shifts for radar and beyond using an E&M wave representation. We did a part 1, which was non-relativistic case. And then by the beyond, we meant relativistic. And in part 2, that's what we covered, was the relativistic case. And now this is part 3. And this is a review plus a little bit. So first thing I want to go over is the case of the Doppler for the radar, for both the non-relativistic and the relativistic case. So here's our radar, and it's putting out a wave. Frequency of the wave is f0, and the wavelength would be lambda subzero. And out here is a radar target of some kind, moving with velocity v. And when the target's relative to the radar, when the target is moving along the line of sight of the radar and away from the radar, the velocity is positive. When it's moving back towards the radar, the velocity is negative. And so what we found was where the frequency received by the radar, the wave goes out, hits the moving target, comes back to the radar. This is the received frequency. Let me start down here. And for the non-relativistic case, what we had was this was equal to f0 times 1 minus v over c minus 2v over c plus v squared over c squared. And in actual radars, the velocity is so small compared to the speed of light c that this term, from the point of view of the radar engineers, is not needed. And so we'll say for the radar engineers, they like to think of it as f0 times 1 minus 2v over c. And if you want to write that in terms of wavelength, multiply through by the f0, you'll get f0 minus f0 over c will give you 1 over lambda, so this is equal to 2v over lambda. And this is the frequently quoted Doppler shift used by radars, minus 2v over lambda. The relativistic case was still f0 times c minus v over c plus v. And what we did this division to expand it out so we could see how the terms in the relativistic case compared with the others. So if we do that, we'll have f0 times, due to division, we'll get 1 minus 2v over c plus 2v squared over c squared minus 2v cubed over c cubed plus 2v to the fourth over c to the fourth. And you can see what's happening all the way down the line. So if you do a comparison between these, you'll see we all, in the radar engineering case, in the non-relativistic case, we have, of course, the f0. And then the second term, 2v over c, 2v over c, 2v over c. And then comparing the non-relativistic to the relativistic case, we have a v squared over c squared here, which is approximately this term except for the factor 2, and then the relativistic case has those other terms. Now I want to show you what these look like if we plot them out. So if we come over here, we're showing the non-relativistic and the relativistic Doppler radar frequency, and the frequency is normalized. So we're taking the F0 we have here and dividing through by F0. So it's F over F0, F over F0. So 1.0 corresponds to F equaling F0. 0.2 corresponds to F equaling 0.2 F0. So this is the radar engineering case. This is the non-relativistic case, and this is the relativistic case. And this is plotted in velocity in units of c. So here v is equal to 0.2 c, here v is equal to c. And we're not going to go beyond c. We don't want to break the speed limit. And what you can see is when the velocity is small, all three agree. The radar engineering one is just a straight line with slope of -2. And you can see the curvature effect from the v squared over c as v gets larger for the non-relativistic case, and this is the relativistic case. And it's interesting that both are equal when v is equal to c. So that's what they look like plotted out. Now if you would take a look, I did that plot there for the receding case. V is positive. But you could also do it for the approaching case. And in that case, if we start at this point here, we would see the radar engineering one and the non-relativistic one, and then the relativistic one going something like that on the negative side. But since things in the universe move away from one another, I didn't want to include that part here in great detail. All right, now if we take a look at this example that we showed earlier, slightly refined. And we want to use this to introduce the idea of the parameter z, the redshift parameter z. That is defined as lambda minus lambda 0 over lambda 0. Again, lambda 0, in the case of the radar, that's the wavelength that's being transmitted. This is for a one-way path. So for a case in which, let's say, we have a vessel out in space, represented here by the Enterprise, because we want to get close to the speed of light but not exceed the speed of light, and it's coming up on a red light in space. Cross traffic, the light is green, the Enterprise is coming up on a red light. And we want to find out at what speed would the Enterprise have to be moving in order for the red light to actually appear green. So the Enterprise is going to run a red light because they think it's green if the speed is right. And the speed that we would be looking for, looking at the parameter z, here's the lambdas, we can substitute in for the frequency. And if we do that, we'll find out that we get f0 minus f over f instead of lambda minus lambda 0 over lambda 0. Of course, when the frequency increases, the wavelength decreases and vice versa. And that's the reason for this sign difference here. And in the one-way case, which is what we're dealing with, the radar was the two-way, this is the one-way. The frequency was f0 times 1 minus v over c. And if we make that substitution, in the numerator here we'll have 1 minus 1 plus v over c, so we'll just have v over c in the numerator. In the denominator, and the f-zeros will cancel out. In the denominator we'll have 1 minus v over c, but v being small compared to c, we can ignore that and we get v over c. Another way to look at that is if we did the Doppler shift in wavelength instead of frequency, we would have the wavelength lambda equal to lambda 0 times 1. And since, as I said, the wavelength increases when the frequency decreases and vice versa, it'll actually be a plus v over c. And you can see if you take the lambda 0 times 1 plus v over c, put it in here for lambda, then we'll have a minus lambda 0 over lambda 0. The lambda 0's cancel out. We get a 1 minus 1 canceling out, and all we're left with then is v over c, which is what we have here, v over c. So now here's the Enterprise coming up on the red light, and we'll assign a wavelength of 650 nanometers to the red light. That corresponds to a line close to one of the hydrogen lines. And we want to find out what the speed has to be to make that light green. So for green, we're going to use 550 nanometers. That's a line in the mercury spectrum, close to a line in the mercury spectrum. So the wavelength that's being emitted is actually 650. So the lambda 0 is 650 over 650. And the wavelength we want to get to is 550. So how do we get to see that? We have to have a speed v over c equal to this. And if we work that out, v will be equal to minus 0.153 times c. So if the Enterprise is traveling roughly at 15% the speed of light, coming up on a red light, the red light will actually appear green. Of course, the Enterprise, we assume, is equipped with a rear viewer, a rear screen. So if after we pass the red light, we look in the rear viewing screen, what would we see? Well, the velocity hasn't changed, so the z value will be the same, but now the sign changes because now, in this case, we're approaching, and after we pass, we're receding. So we need to have a number here, which when subtracted from the 650 will give you a positive 100. And that number is 750. And so if you would look in the rear screen after you pass the red light, the actual real red color would be shifted to 750 nanometers, and that is just barely in the IR part of the spectrum. Now what we want to say a little bit about is the cosmological redshift. First I got to grab a little piece of tape. Okay, so we want to say a little bit about the cosmological redshift. So the idea here is we have a galaxy and we have another very distant galaxy. And those galaxies, they seem, if this is the Milky Way, and we're looking out at this very distant galaxy, it seems to be receding. The reason it's receding, it's not like the radar and the aircraft target where they were receding from one another in space. The reason these galaxies seem to be receding is because the space between them is expanding. And so when this galaxy emits some light, that light, particular wavelength, goes through the expanding part of space and get stretched out. That is the cosmological redshift. That is not the Doppler shift. It's the cosmological redshift. So based on this, I think you can see that you can't apply the Doppler formulas to the redshift values of z and get a true recessional velocity for the galaxies, because this is not a Doppler effect. This is an effect from the expansion of space. And in order to explain this, you need a model. And the model, you need a model for the universe. And over here, we're showing the Einstein-de Sitter model for the recession velocity of galaxies associated with a now and then, which I'll explain, compared to the Doppler formula. So here's the Doppler formula. This was the case that we showed earlier, where the velocity in the non-relativistic case for the frequency was equal to z times c. And earlier in part 2, we had worked out the relativistic velocity, and that's this formula over here, a little more complicated in terms of z. So if you use the value of z, this was what you would say the recessional velocity is for the non-relativistic case, and substituting the same value of z in here, that's what the relativistic velocity would be. But they're not recessional velocities because it's the expansion of space that we're talking about. So here's the equations for the Einstein-de Sitter model. And the Einstein-de Sitter model is a model that says that space just keeps expanding. So you start out with a big bang and space keeps expanding. And the analogy that I like to make for the Einstein-de Sitter model is, you know, if you have a rocket that you blast off from Earth, you have to attain certain conditions for that rocket to basically go to infinity. And that's what happens in the Einstein-de Sitter model. It starts out with a bang, and it just keeps increasing, increasing, increasing all the way out to infinity. It's a model that has zero curvature. But now let me explain these two velocities. Here we have the Milky Way. Here we have a galaxy that we're looking at, and that galaxy emits some light. Since space is expanding, by the time that light reaches the Milky Way, this galaxy is now located further away because of the expansion of space. So when this light was emitted, that was emitted in the past. That's considered the then. That's when the light was emitted. When the galaxy gets over here, that's when the light is received back at the Milky Way, and so that's considered the now. So this is the then. This is what the galaxy had a particular velocity here, v then, when the light was emitted, and this is what the velocity would be, v now. And so they are plotted here along with the non-relativistic and the relativistic formulas, plotted as a function of z, the redshift, and with the recession velocity in units of c. So with 1 right here, that means v would be equal to c, and that's this dashed line across here. The relativistic line never gets to that limit of c. The non-relativistic one really doesn't make any sense. They're all equal at very small redshift, but what is really interesting is that from the Einstein-de Sitter model, the now and then case for sufficiently large z actually allows for recessional velocities that exceed the speed of light, as you can see. So if we come over here now, the point is cosmological redshift is not Doppler shift. So if we come over here now, in the book by Peacock called Cosmological Physics, if you go to page 72, he says, it is common but misleading to convert a large redshift to a recession velocity using the Special Relativistic Formula, which is a slightly different version than what we use, but it's the same. Any such temptation should be avoided. In other words, you can't use these values of z to say that, from the relativistic formula, to say that this is what the velocity of the galaxies would be. Any such temptation should be avoided. On 87 he says, nevertheless it is all too common to read the latest high redshift quasar as receding at 95% the speed of light. If you're using the relativistic formula and z is increasing, you get closer and closer to the speed of light, but you can't ever reach it because of the formula relativistic velocity. If you go to Harrison, Cosmology, go to page 236, the truth is that expansion redshifts are totally different from Doppler redshifts, which is what we've been saying. And the velocities cataloged by astronomers are not the recession velocities used in the velocity distance law. We didn't talk about that, but that's Hubble's law. On page 240, he says, it is a regrettable practice that creates confusion and ensnares the unwary. The damage done, however, is that students believe that this is the correct method. So the point is, the cosmological redshift is not a Doppler shift.